my recent paper, which is the fact that only classical states have optimal measurements. Obviously, I'll talk more about that. First of all, I think I should just say, if you have any questions or anything's not clear, please just like unmute and ask a question. It's online and I can't see any of you, so I have no idea if what I'm saying is going to make sense to anyone or not. So yeah, please just unmute and ask away if anything's not clear. Okay, I can see some other people joining, but I guess I'll start. Yeah, so I mean, here is the archive link if you're good at remembering numbers, and it's joint work between me and my two supervisors, so Sergei Strelchuk, who's a member of the maths department, and David Arvidsson-Shakir, who's a member of the physics department and Hitachi Cambridge Laboratory. Okay. So we're going to start with basically a quick review of classical parameter estimation. So nothing to do with quantum, but it's basically the foundation for the field of quantum metrology. So as a simple example, let's talk about proportion estimation. So that's when you have some large number of people n, and you want to estimate the proportion p, say who like cheese, or some other property that you'd like to estimate how many people satisfy this property. If you don't necessarily have the resources to ask everyone, you know, there's 8 billion people in the world. That's a lot of people that you have to ask. You will probably ask some smaller sample of n less than big N people, and then you will receive some sample from the binomial distribution with little n trials with the proportion p, where you don't know the proportion p, but you know you're going to be sampling from the binomial distribution. It's worth pointing out there's no correct way to then infer p from that sample. You can place some bounds on p in this case. You can say it's definitely greater than or equal to something, or definitely less than or equal to something, but you can never say exactly what p is, because obviously you haven't asked everyone, so you don't know for sure. But most people would probably estimate the proportion of the sample that said yes. So you would look at your sample from the binomial distribution, and then you would say, okay, let's say 40 people said yes, they like cheese, and I asked 60, I'd estimate 40 over 60, or 2/3. We'd like to quantify, you know, we want to do some maths, so we have to come up with some way to quantify how good of a guess that was. And most people tend to take this number here to kind of summarize how good that guess is, which is called the least squares estimate. Oh, sorry, the least squares loss function, which says, okay, I'm going to measure how good my answer was by its distance squared to the true value. And I can't know what that is because I don't know what the true value is, but I can estimate what it would be for every single value of the true value, which we'll come on to later. So the general case of parameter estimation, which kind of is supposed to mirror the proportion estimation case, we have some parameter theta, some abstract parameter that lives in some abstract parameter space, big theta. Almost always this is just some subset of r to the p for some number p, because we describe things with real numbers as humans usually. We observe some random variable x, so we observe the outcome of some random variable x. Before it was a binomial distribution. In general, we don't know what the distribution is, but we do know that it depends on theta, and we know what the distribution would be for every single value of theta. So we observe some outcome little x of the random variable x, and based on that outcome, we make some guess of what we think the parameter is. So over here, it was little x divided by n. And then we have some loss function L of theta1 and theta2, which tells us how good our guess was. So here it was the difference between theta1 and theta2 squared. It could be something else in general. People sometimes use relative entropy or things like this. And it's measuring how good our guess was. Hopefully everything on that slide makes sense. Please do unmute if it doesn't. Okay. So as I was saying, when we talk about how good an estimator is, if we decide on some particular function theta hat of x, and we say, okay, this is what our estimation strategy is going to be, we want to be able to say how good that estimation strategy is. We want to be able to quantify it. But the problem is it depends on what the underlying parameter is. We don't know beforehand how good our estimator is going to be, because to do so, we would have to know the parameter to begin with, and we wouldn't have a parameter estimation problem because we'd already know the parameter. So instead, we introduce some risk function, which depends both on our estimation strategy and the parameter. Can you see my cursor, by the way?
Yes.
Okay, thank you. So it depends on the estimation strategy and the parameter. And that loss function is the expectation of, the risk function is the expectation of the loss function. So if the true parameter were theta, then what would I expect for my random variable in the case that the true parameter is theta? What would I expect the loss of my estimator to be? So it's saying that again, it's how well will I, or how badly do I expect my estimator to perform if the true value was theta, according to my choice of loss function, which is very often the least squares loss function. For example, before with that proportion estimation, if I take this estimator to be x over n, then you can, and the loss function to be least squares, so just what I had before, then you can calculate the risk function. And because this thing is kind of related to the binomial distribution, it kind of has like the binomial distribution variance of p times 1 minus p divided by n. So this estimator will do extremely well for small values of p and p close to 1, and it does worse in the middle of the half. This is plotted for, I think, n equals 1. And as n increases, it kind of uniformly, the risk function is going to go downwards. So we're going to get better and better estimates with high probability because we expect the loss function to be smaller and smaller as n goes to infinity. Admissibility. So given that we can kind of quantify how good an estimator is, we can ask, when is one estimator better than another? And the answer is it depends on the underlying parameter, right? It doesn't make sense to say estimator A is better than estimator B without referencing a particular parameter, except for the one case like this, where let's say we've got two estimators, theta hat and theta tilde, and theta tilde's risk function is below theta hat's everywhere. Then we can say that theta tilde is better than theta hat, because whatever the value of the underlying parameter, we always expect to do better. If that doesn't happen, then we can't say that theta tilde is better than theta hat, because there's some values of the parameter where one does better than the other, and some values of the parameter where it's the other way around. If this happens, then the terminology that people use is we say that theta tilde dominates theta hat. It's worth pointing out that that's an extremely strong condition. So, for example, if we take this kind of cartoony picture of two risk functions where theta hat is very bad almost everywhere, well, not almost everywhere, but for most of the interval, and theta tilde is looking like it will be much better, but there's this very small part here where theta tilde does actually worse. We still can't say, or we can't promise that theta tilde is better than theta hat, because if we were to be so unlucky that the parameter was in this region here, then it would be that theta tilde was worse than theta hat. So it's a very strong condition, and to emphasize, we can't promise one is better than the other. If we had some more knowledge about our parameter, say like we thought it was distributed in a certain way, or we could be sure that it wasn't in this problematic area, then maybe we could. But if we have no knowledge of our parameter before the experiment, which is kind of the most realistic approach, we can't promise that theta tilde is better. And then again, some terminology. An estimator is admissible if nothing dominates it, and it's called inadmissible if there's something that dominates it. It's worth pointing out that admissible doesn't necessarily mean good. It's more that inadmissible means bad, because if you're inadmissible, then by definition, there's an estimator that's better everywhere in the parameter space. So why would you use the inadmissible estimator? You'd just use the one that was better everywhere in the parameter space. There's an asterisk here because maybe in some cases you can argue that an inadmissible estimator is still good because it's particularly simple or something. but you would have to usually give a very good reason why you would want to use an inadmissible estimator. Okay, and then finally, because we're going to talk about optimal measurements later, it's worth kind of, for comparison, talking about what would an optimal estimator look like. So, given the previous definition of one estimator being better than another, when is an estimator optimal? And the only way we could have an estimator being the best estimator is if for all other estimators and for all values of the parameter, its risk function is less than or equal to the other estimator's risk function. So this is, this would be the best strategy, unambiguously the best. If for any other strategy that we chose, we would always do at least as well. This is an extremely strong condition. And if you notice, for example, the constant estimator, so regardless of the outcome of the experiment, always guessing theta 0, well, that by definition has zero risk at theta 0. Sorry, this should say risk of theta hat at theta 0 is equal to 0, because at theta 0, because we're always guessing theta 0. So if the true parameter were theta 0, we would always say theta 0 and would have zero risk. So if an estimator is optimal, given the previous definition, we would need it to have zero risk everywhere, because it would need to have risk less than or equal to 0 at every single point of the parameter space. I mean, we always get the right answer, i.e., our parameter estimation problem isn't really a parameter estimation problem. It's deterministic. Nothing really random is going on. So in every application, this never happens. So, for example, it's impossible if theta is infinite, because we only receive finite data. So, we could be sure that this doesn't happen, basically. So the point is to say that optimal estimators just don't really exist. If you want to talk about an optimal estimator, you have to make some additional modeling assumptions where you assume that your parameter is more or less likely to be in different parts of the parameter space, or you take some kind of asymptotic limit where you receive infinitely many copies of the same random variable.
Sorry.
Okay. Yeah.
One question. Sorry, I get lost about the constant estimator. Do you mean the constant estimator is always the best, or I missed the point?
Okay, yeah. So what I'm saying is the constant estimator is not a good estimator in almost all cases, right? Because you ignore the outcome of your experiment, this little x, which is the realization of your random variable, and you just guess theta 0. So that would be like in the proportion estimation example, I ignore how many people said yes or no to my survey, and I just always guess a half. And that's kind of a stupid thing to do, but the important point about it is that if the true parameter were a half, then I would always get it right. So at the point theta 0, maybe if I quickly edit my slide to have the right notation, it will become clearer. Sorry, I apologize for this. I guess probably see my but yeah, so because they have zero risk at exactly one point in the parameter space, which is the point at which the constant estimator is. So right, yeah, sorry about that. So here we see the risk of the constant estimator always guessing theta 0 has zero risk at exactly the point theta 0. Because if in my proportion estimation example, I always guess a half, if the true proportion was a half, I'd always get the right answer, kind of trivially, right? Now, if there was some optimal estimator, okay, it's called theta hat as well, but pretend that we hadn't defined the constant estimator. If someone came up to you and was like, here's the best strategy that you could ever do, theta hat, we would need for all other estimators and for all values of the parameter space that this would have lower risk everywhere. But the problem is if I take theta tilde to be theta 0, then it has zero risk at theta 0. So I would need theta hat to have zero risk at theta 0. but I can do that for every single value of the parameter space. So theta hat has to have 0 risk everywhere. And then I'm just kind of making the point that that's never going to happen, because in that situation you can always get the right answer. So you're not really doing an experiment. There's not really anything probabilistic going on. It's all deterministic, because you can just look at the outcome of your experiment and calculate exactly the right answer. And that's impossible if your parameter space is infinite, for example, which is usually the case. Does that make sense?
So you mean there is always a point they can achieve 0, but we can never know, basically.
Yeah. So the constant estimators always achieve 0 at some point in the parameter space. We just don't know. We don't know the value of the parameter before the experiment, so we don't know what the risk is going to be. But if someone were to propose an optimal strategy, because the constant estimators exist, it would have to have 0 risk everywhere.
Okay, I see. Okay, thank you.
No worries. Okay. Now we're going to move on to the quantum state case, which is kind of going to add another layer to this of measurements. So now we're given some quantum state that depends on a parameter. So for example, the thermal state depends on the inverse temperature, like this. So the inverse temperature would be our parameter, or the temperature, depending on how you wanted to parameterize it. And we want to estimate our parameter. How are we going to do that? Well, we're going to do some quantum measurement, because that's the only way to extract information from our state. So we could do a projective measurement, or more generally, and kind of the correct way of describing it mathematically, we do some generalized measurement, or POVM, which is indexed by some outcomes from 1 to, let's say, little m. We're going to see some measurement outcome I. So when we do the experiment, we will receive some measurement outcome, and then as before, we make some guess theta hat of I of our parameter. So this is the estimator. And note that it explicitly depends on the measurement choice, because the things that the inputs that this estimator is going to take are going to be the output, the possible outputs of this POVM. In each of the different possible outputs of our measurement, we're going to make a potentially different guess of our parameter. So just to summarize, some parameter living in some parameter space, we get given a quantum state. We pick a measurement and an estimator. We pick a loss function, and as before, we get a risk function, which is the expected loss of our estimator at the point theta. So I think that's a summary of the quantum case. Does that make sense? No one has unmuted, so I'll assume so. As a quick side note on kind of the level of generality here, it looks maybe simplistic to have one state and one POVM. To begin with, what if you've got multiple parameters, so like temperature and pressure, for example, rather than just temperature? Well, that's easy to deal with. You can just make your parameter space contain vectors. So for example, just take r squared, and then kind of by definition, you're encoding 2 parameters in when you talk about a vector in your parameter space. Copies of a quantum state. So realistically, in an experiment, you're not going to do a copy on a single quantum state. You're going to receive lots of copies of a quantum state. So we're going to receive sigma n times, but and we're going to do lots and lots of experiments, and then we're going to do some post-processing on our data. We're probably going to do some averaging, and then we're going to make a guess of our parameter. But actually, that's included in our model already for free, because you can just take the parameterized state rho as n copies of sigma, and kind of by definition, it's almost trivial by the notation. Now we're dealing with the case where we've got n copies, and we can do a POVM that factorizes as measuring each one of those individually, and then we've just got some POVM that's indexed by a vector, and the framework works the same. And then finally, adaptive strategies. So in the case where you've got like n copies, you might measure the first copy, and based on the outcome, you might choose a different measurement to do on the next copy. And actually, this is probably very likely if you're using something called the quantum Fisher information, you will almost certainly do this. If you don't know what that is, don't worry. But again, kind of by mathematical notation trickery, which I haven't bothered to go through in detail, but it's very common in quantum information theory. You can actually just combine adaptive measurements into a single giant POVM. You can kind of just stick them next to each other. So we actually cover this case as well. So this is just to point out that the almost simplified framework of receiving one quantum state and doing one measurement and then making a guess covers lots more things than it might seem at first. It can cover multiple parameters, it can cover multiple copies, and it can cover adaptive strategies as well. Hopefully that makes sense. Okay, so kind of onto the main point of this is, okay, so we worked out how to compare estimators, but how can we compare measurements? When is one measurement better than another? And again, the key point here is that even if you use different measurements so that the estimators are defined as functions on different spaces, because there are different number of outcomes for each of your measurements, you can still compare their risk functions. Because risk functions are a function from the parameter space to the real numbers, which tell you how bad would this estimator do at this value of the parameter. And it doesn't matter what measurement you do, your estimator has to be defined for every value of the parameter. And we're going to do the same thing as admissibility. When can we promise one measurement is better than another? So we're going to do it we're only going to say one measurement is better than another if we can absolutely promise that it's better, regardless of the underlying value of the parameter. So kind of one way to illustrate when this is true, we're going to have a game. This isn't really something that would happen in real life, but it's meant to illustrate when we can promise one measurement is at least as good as another. So let's say Alice picks her measurement M, and then Bob picks his measurement F and his estimator theta hat F. Then if Alice can pick, based off what Bob chose, an estimator theta hat M such that its risk is everywhere less than or equal to the risk of theta hat F, then we can say that this measurement M was at least as good as this measurement F. So I mean, here's just that illustration before where theta tilde and is less than or equal to theta hat everywhere. So I'll kind of repeat this again. We're saying that this measurement M is at least as good as this measurement F, because whatever choice Bob makes for his estimator, Alice can make a choice theta hat M and say, well, my estimator is at least as good as yours. So if this happens for any choice of theta hat F, then we can say that M is at least as good as F. And I've kind of written this out again in the next slide. So this is just a copy of that diagram from before, and now I've written it out. So a measurement M is at least as good as a measurement F, written like this with this funny kind of curly less than or equal to sign. If for any estimator based off F, there's an estimator based off M, such that for all theta in the parameter space, the risk of theta M is less than or equal to the risk of theta F. So it's kind of another way of phrasing it is, if you were to choose the measurement M instead of F, you would never regret it, because if later on, after you've done the experiment, you go, actually, I wish I'd done the measurement F and used this estimation strategy instead, that's okay, because you can find some estimation strategy theta M that was based off your original measurement that does at least as well everywhere. So you will never regret switching your measurement from F to M. And it's also worth arguing, this definition is a very strong definition, but it's in some sense the only definition you can make at this level of generality. Because if this is not true, if M is not at least as good as F in this notation, then you can regret doing the measurement M instead of F, because if later down the line someone goes, oh, actually, I wish I'd done this estimation strategy instead, this F and theta hat F, then you're not going to be able to, there's at least one case where you're not going to be able to find an estimation strategy based off your measurement that does at least as well everywhere. So there'll be some values of the parameter space where you expect to do worse. So if this doesn't hold, you can't say that M is at least as good as F without making some additional modeling assumptions. So talking about how your parameter is distributed or taking some kind of asymptotic limit. Hopefully that definition makes sense. The key point is that it's a strong condition, it's very operationally driven, and it's kind of the most general definition you could make at this stage. This like immediately just gives us a definition of an optimal measurement, because when we say something is optimal, we just mean it to mean it's at least as good as any other measurement f. It may be a little bit counterintuitive. The better measurement goes on the left-hand side of this curly symbol, which is maybe not the way we're used to things. The reason that's true is that the inequality with the risks sits this way round. So to have the inequality kind of the same direction, we write it like this. But remember that the measurement on the left is the one that's better than the one on the right. Its risk is less than or equal to everywhere. This is a very strong condition, just like before when we talked about optimal estimators. That was a very strong condition. This is an extremely strong condition as well. It's not immediately obvious that this kind of can't happen, because when we talked about optimal estimators, we basically concluded they don't exist. So it would not be surprising to find that optimal measurements don't exist as well. But as it turns out, and is kind of spoiled by the title of the talk, yes, optimal measurements do exist. So here's two conditions for an optimal measurement to exist. The loss function is convex in its first argument. So this is kind of like a technical definition on the loss function. This is true, for example, for least squares. So lots of people only care about least squares. So this condition is kind of, they don't care about it. If not, then, almost all loss functions that people care about satisfy this technical condition. And there's good reasons for that, but I won't go into that. And the second thing that you need is that your state is classical. So to talk through those in detail, convexity, you've probably all seen it before, but this means that if you fix some probability distribution and some corresponding values of your parameter in the parameter space plus another one phi, then you have this inequality. So it's sometimes said that the function is below the chord. So the function evaluated at this kind of averaged value here is less than or equal to the average values of the functions. So you've probably seen this before. If you haven't, then it's just some kind of technical inequality. We're going to use it in a second, so I've written it out here to be explicit. But if you haven't seen it before, just least squares satisfies it. So most people they feel like this condition isn't really adding anything on because they already have it. Second thing I said is that the state needs to be classical. So what exactly do I mean by classical here? I mean that we can fix some orthonormal basis that doesn't depend on the parameter theta. And then my state just looks like a classical mixture of those. So it's diagonal in that basis. And the only thing that changes are the diagonal entries, and they can be functions of the parameter. So in some sense, I don't have any quantum coherences or entanglement or anything interesting. My state is just some classical probabilistic ensemble, which doesn't depend on the parameter. For example, the thermal state from before satisfied this with the energy eigenvalues. Another example that we did in the paper is if you're trying to estimate depolarizing noise and you put in some pure state, then the state that you get out is also classical.
So does this conclusion depend on the dimension of the theta or the form of the theta?
No, it doesn't, as we'll see in a minute. So this is true in the multi-parameter setting as well. So if you take a vector space, this is also if you take theta to be vectors, this is also true.
Okay.
The converse, which we'll talk about in a minute, is requires another assumption. But for now, as we'll see on the next slide, the proof is actually very simple.
Okay.
So here's our classical state. Let's take the kind of obvious measurement. So we're just going to do a projective measurement onto this eigenbasis. Let's take some other measurement. If you remember our definition of optimal, we have to show that M is at least as good as F. So suppose as well we have some estimator based off F, then we need to find one based off M that does at least as well everywhere. So this is the one that we're going to pick, which initially looks a bit complicated, but the idea is in the case of outcome I, we kind of simulate the measurement F on each of the on the basis vector I, and then in the case after simulating that measurement, we say what theta f would have said. So kind of repeating that, if we get outcome I, we kind of assume that our state was in, let's say we get outcome 1, we kind of assume that our state was actually 1, and we say, okay, imagine doing the experiment with 1 and using this estimator f, and what would we get in each of those cases? And this doesn't depend on theta anywhere, so this is fine. Okay, then if we look at the risk function of m, well, it's the point theta. It's the probability of getting outcome I times the loss function evaluated if we get on our guess of So if you remember, this is the expected value of the loss at the value theta. So we sum over the measurement outcomes and we say, okay, what's the probability of getting measurement outcome I times the loss function of this is what we guess in the case of I with regards to theta. So this is just expanding the expectation as an explicit sum over probabilities. And this, if you notice here, this is just theta hat m of I. Maybe I should have written that in as an extra line, but I've written it out in full detail. Now, if you remember, we assumed that our loss function was convex in its first argument. So in particular, this here, this trace I fk, this is a probability distribution over k, because as we sum these up to the identity, these sum up to the identity, which gives this trace being 1. So by convexity, we can say less than or equal to and pull this sum out like this. But then if you look at this sum over I, we've got exactly the state rho because the trace is linear. So we have the sum over k of trace rho fk times the loss function of theta fk at theta, which is exactly the expectation of the loss of theta hat f. So it's the risk function of theta f. So theta hat m is, this should have a hat on it, sorry, has a risk function that's less than or equal to theta f's everywhere. So it's better. So yeah, this holds regardless of our there's no assumptions on the parameter space here, so you could have 1,000,000 parameters, that's fine. Yeah, and there's no best estimation strategy, and estimation strategies get very complicated as you make your parameter space very, very large. But we can kind of compare these measurements without reference to a particular estimation strategy, because we know whichever one you pick, whichever theta f, you can always find one based on m that's at least as good everywhere.
I have a question about that. So for here you have mi. What does that mean by mi is a measurement?
Yeah, so yeah, exactly. So
but here we have 2 measurements, right?
Yeah, we do. So we have mi and we have fk. So I've just indexed them with different letters.
So can you help me to understand why there are 2 measurements here? Because we know that trace I fk could be mean that you measure fk. Wait, I don't understand why the measurement could be composed of 2.
Yeah, okay. So why are we talking about 2 measurements? So we're trying to show that this m is optimal. And if you remember the definition of optimal measurements, I'm trying to go backwards quickly.
The definition is that you can get the value without any deviation from the ideal value, right?
No. So the definition of a measurement being optimal is that it's least as good as any other measurement f. And a measurement is at least as good as any other measurement f is. All we're doing in this proof is we're kind of we're putting this out in detail. Is m is optimal if any estimation for any measurement and estimator I pick, any different measurement and different estimator that I pick, I can pick one based off my optimal measurement that does at least as well everywhere. Yeah. So if you look at the steps of the proof, this is exactly what we're doing. We've written down what m is explicitly. We've then assumed there's some other measurement f that we don't know anything about, and some other estimator based off f that we don't know anything about. We just know they exist. Yeah. And we've constructed theta hat m such that it has lower risk everywhere. So we can conclude that m is optimal. So if I put up the proof again, I'm trying not to go to the next slide, then you can see that we've written down we've written down M, we've assumed some general other measurement and estimator, we've written down a strategy theta hat M, and we've shown that it has lower risk everywhere.
Mm-hmm.
Does that make sense?
Yeah, maybe we can talk about that later.
Okay, we can talk about it then. Yeah, sure. Okay. So in this case of classical states, we do have an optimal measurement. The question is, are there any other interesting cases? And I spent a long time trying to find them before I kind of became pessimistic and tried to start proving that there weren't. And as it turns out, there aren't. So here we've got some additional assumption about the parameter space, but suppose that L is least squares. So we're kind of specializing to that case. I do think that it's true for more general loss functions, but I don't know how to prove it. Suppose that our parameter space is convex. Again, it can be multi-parameter, so it could be vectors, and that there's some, and that our state has some optimal measurement. Then we can conclude it's classical. It's worth noting this condition here about convexity can be made weaker. I think it's true, for example, you could modify the proof to deal with any open set. You can do the disjoint union of convex sets. Almost all parameter spaces of interest are kind of like products of intervals, so they're convex. But you can make this weaker if you come up with a particularly strange parameter space that's still physically relevant. This theorem probably still holds with just some minor modifications at the end of the proof. So essentially, kind of to answer the question, when are there optimal measurements? It's if and only if your state is classical. In the case of least squares, probably in the case of other loss functions as well, but as I say, I haven't proved that. The proof is very long, so I'm not going to go into the details of it here. It's in the paper if you want to read about it. The main idea is to kind of say if there is an optimal measurement, then it has to be optimal if I fix two values of the parameter, theta 1 and theta 2. Then because my measurement is optimal, it has to kind of be optimal for the binary decision choice of giving theta 1 or theta 2 as well, because that's like a subset of the original problem. And that problem is something that's well understood. So it kind of, we reduce to that case and then study that case. It's slightly different from conventional state discrimination because you can guess values of the parameter that are kind of in between the state, but you know, the analysis kind of carries through. It's worth just very quickly spelling out the implication of the fact that there's no optimal measurement. It means that if we play this game again, then whatever measurement Alice picks, so let's say Alice picks some measurement M, Bob can pick a strategy. So he's going to say, okay, given that you're using M, I'm going to pick F and theta hat F. And whatever value of the whatever strategy Alice picks, Bob can pick a value of the parameter and say, I expect to do better there. So it's quite a long chain of quantifiers here. Basically, Alice can't be sure that she's going to do better than Bob. If Alice has to go to her boss and say, can we be sure we're going to beat Bob? She has to say no, because if Bob were to do this, then whatever they chose, there's always some values of the parameter where they expect to do worse. And if everything's continuous, which it probably is, then you can kind of extend this to, because it's this being true at a point means that it's going to be true in some small interval as well, if things are continuous. Okay, so for the last kind of maybe 5 minutes, I'll talk about an approximately optimal measurement. So most parameterized states that people care about are not classical. Lots of them are pure, for example. So there's not going to be an optimal measurement. So can we kind of put some epsilon in there and do an approximately optimal measurement is a question that's kind of interesting. And there's two cases where we might be very hopeful that approximately optimal measurements exist. The first one is kind of an analysis style thing where if our state is close to being classical for some notion of closeness that we'll talk about later, then maybe there's an approximately optimal measurement because, you know, classical states have optimal measurements. If we're close to classical, maybe we're close to optimal. And secondly, in some large number of copies limit. So in the asymptotic limit where we're receiving kind of n copies as the same state and we're taking n to infinity, And that's kind of been studied before. And if you know what the quantum Fisher information is, that's exactly the realm of the quantum Fisher information. But we haven't actually managed to deal with this second case yet. So it's an interesting open question. So yeah, to begin with, we have to just be precise about what we mean by approximately optimal. And there's kind of three classic ways of, three obvious ways to define it. So firstly, we can define it with respect to an additive error. So I've written out the definition here, which is a bit intimidating, but essentially it's exactly the same definition as before, but now there's a plus epsilon. So it's epsilon additively optimal if for all other measurement estimator pairs, so for all of Bob's choices of f and theta f, Alice can choose some theta m such that for any value of the parameter, the risk is of theta m is less than or equal to the risk of theta f plus epsilon everywhere. So we accept that we're not necessarily going to be better everywhere, but we're going to be better, if epsilon is small, we're basically better everywhere, or at least as good everywhere. Multiplicative error is a very, similar thing, except now that we, instead of saying that we're plus epsilon, we introduce some small parameter eta, and we say that we're less than or equal to 1 plus eta times the risk everywhere. So in particular, if you're talking about the asymptotic limit, where you're caring about as kind of n going to infinity, very often you're interested in how things are scaling with n. And in that case, you're going to be interested in the multiplicative case, because as n goes to infinity, your risk is tending to 0 anyway, so this kind of additive error thing is going to become trivially true. Finally, there's this idea of a localized error where, okay, maybe we're optimal basically everywhere, but there's some small set that things go wrong on, which we can kind of make rigorous by saying it's delta locally optimal if for all other pairs there exists an estimator and some small subset S. So things are allowed to go bad on this subset, but for anything not in the bad subset, we're at least as good, and this bad subset is small. So here's kind of three ways that you could define an approximately optimal measurement, depending on additive errors, multiplicative errors, or localized errors. We can combine these, so it's where you could talk about your epsilon additively optimal, except on some delta locally bad set. So you could kind of combine definition 1 and 3 or definition 2 and 3 and say that this condition has to hold everywhere except on some small subset S. And we're probably going to want to end up doing that because at some points in the parameter space, we might have 0 risk. And, with 0 risk, for example, you're never going to be able to have this multiplicative error. So you might want to say you've got in the asymptotic limit, you've got kind of some small multiplicative error tending to 0, and except on some small set which is also tending to 0. And then kind of 3 somewhat interesting results we prove in the paper, which is what you might expect, is that we kind of get 3 different, if you're close in some notion of close to a classical state, then there's a close to optimal measurement result. So if rho of theta is close to some classical state in trace norm uniformly in theta, so basically the trace norm of rho and theta and sigma and theta is less than or equal to epsilon for every value of theta in trace norm, then there's an additively approximately optimal measurement. So that's the first thing, where you have a kind of plus epsilon on your risk. If you're instead close in maximum relative entropy, which is just a version of kind of relative entropy, then there's a multiplicatively approximately optimal measurement. And then finally, and kind of trivially, if rho of theta is classical except on some small bad subset S, then you can say that there's a locally approximately optimal measurement. It's an open question to find a state that's far from classical, but that does have an approximately optimal measurement, or to prove some result that says if there is an approximately optimal measurement, you're approximately classical. I think that there should be a state that's far from classical that has one. So in this kind of many copies limit, where you take many copies of a pure state, there's been lots of work on the asymptotic limit in a slightly weaker setting, and people talking about the quantum Fisher information, and it would be nice to match those 2 things up, but we haven't done that yet. Yeah, that's what I was saying. Okay, yeah. So thank you very much for listening. I'm slightly under time, so there's plenty of time for questions if anyone has any. If not, I can go back to bed.
Can we get back, since we have some time, so could we get back to see why there's two measurements at the same time? I just stuck on this point.
Sure. So okay. So I guess we were talking before about when one estimator is better than another estimator.
Right.
So now we want to kind of generalize that and say, when is one measurement better than another measurement? So we're intrinsically comparing two things because we're saying one measurement is at least as good as another measurement, right?
Right.
And the way we do that is with respect to, so if for any estimation choice theta hat based off f, we can pick one based off m, such that this estimator is kind of at least as good as this estimator. So m is at least as good as f if whatever measurement strategy you might pick based off f, you can pick one based off m that does at least as well. So it's kind of it's a way of comparing them without reference to a specific estimator, because you can be sure whatever specific estimator comes up, you can pick one that does at least as well. Does that make sense?
Yeah.
Okay, cool. So an optimal measurement, the kind of the natural definition of an optimal measurement, and what we usually mean by optimal, is that it's least as good as any other choice. So for any other f, we can pick one that's at least as good. Does that make sense?
Yeah.
Cool. So then in this proof, all we're doing is we're saying, okay, assume that this is our state. I'm claiming that this measurement is optimal. So I've indexed the measurement outcomes by I, and it's just the projective measurement onto the basis vector I. Okay. Without less generality, let's say that the I span the Hilbert space. So then we're supposing that f is some other measurement, and to show that it's optimal, we need to show that m is at least as good as f. So we have to introduce some arbitrary estimation strategy based off f. Yep, exactly. And then we have to construct one based off m that does at least as well everywhere. And this is kind of the one that does that.
Yeah. So you construct the estimator of m based on the f, right?
Yeah, exactly. And we're gonna the construction uses this theta of f, and the point is that this final inequality is the risk of theta of m is less than or equal to the risk of theta f everywhere, and it's kind of this just a trivial convexity thing. We just pull this probability distribution out.
I'm just curious about if mi is not equal to pure state. Is that possible?
So yeah, well, that's exactly what this converse result says, which is so okay, I haven't mentioned it, but this is the unique best measurement up to, obviously with a POVM, you could always kind of you could fine grain this, so you could just split one of your things into half plus a half of it. That's
that's pretty good measurement.
And then also, if two of these pi of theta are the same, then you've kind of got some degeneracy, and you can actually measure any kind of projective measurement in this eigenspace. But this is essentially up to trivial kind of annoying edge cases. This is the only best measurement in this case. And then this converse result says that the only states that have optimal measurements are classical ones. So actually this is the only kind of optimal measurement that exists, and it only exists for this very special case.
But as you mentioned before, this is because of right now we identify if that's the optimal measurement is because of a loss function is defined by L2, right?
Sorry, I didn't understand the question.
Okay, so as you mentioned before, and it's because this is the optimal measurement is because of the definition of the loss function, right?
Oh, the L2 least squares?
Yeah. Right. That's a definition from the beginning, right? So but you also mentioned before that maybe it's not if our loss function is not defined this way, right?
Yep. So that's a very interesting question. So, this was with respect to some generic convex loss function. So LP for any P, for example. or the relative entropy. This converse result, we have only proved for least squares. It would be an interest if you managed to come up with a different loss function that or maybe a different physically motivated loss function where you had optimal measurements in the case that rho of theta wasn't classical. That would be very interesting. My intuition is that it won't happen and that it's kind of, I would imagine that you can get a converse result for generic loss functions, but I don't know that. And my intuition is just because it's such a strong condition to require that a measurement is optimal.
Oh, I see. Okay.
But it would be nice to either kind of extend this converse result, where is the converse result, to the general case, or find a counterexample to the general case. Yeah.
Okay, thank you.
No worries. Any other questions?
May I ask for the case of classical state, you have the optimal, but you must choose the measurement to be I basis outer product. But in principle, you don't know the state from the beginning, right? So you don't know what's the optimal I, the basis to choose.
So we usually assume that we do know the state that we're being given. So for example, the thermal state, we would assume that we like know the Hamiltonian, but we just don't know the temperature. So here's, the thermal state. So we would assume that we know this Hamiltonian and therefore we know in theory this state for any value of the parameter. Otherwise, if you don't know the state, you can't really do parameter estimation because someone just gives you a random state and says estimate the temperature. If you don't even know the Hamiltonian, how do you do that? You could rephrase it as a parameter estimation problem with more parameters, where you say that you've got, it depends on the temperature and the Hamiltonian, and you parameterize the Hamiltonian by, I don't know, half nn plus 1 real parameters or something. And then your loss function, maybe you only care about the temperature value. So you could rephrase it as a different parameter estimation problem that's very complicated. But usually we kind of assume that we know the form of the state for any value of the parameter, so that when we come down to this state here, we assume that we know this eigenbasis. We just, don't necessarily know what these probabilities are because we don't know the value of theta. Does that make sense?
Yeah, I see. So basically, you already know how to parameterize the state. That's the assumption.
Yeah.
So
So, I mean, often the way that these states are produced is you'll have some unitary or some CPTP map that encodes your parameter, and you'll put a probe state in. The parameter gets encoded in, and then you get back out your state, and you know what that state is because you know what probe state is, and you know what the probe state was, and you know what that unitary is up to some parameter.
I see. So another question probably is related to this. So there is some classical shadow tomography that can estimate the state.
Yeah.
Right? So does this the classical shadow tomography related to this kind of error estimation approach?
Yeah. So it's exactly so shadow tomography or kind of, I guess in more generality, kind of like full state tomography. That's a special case of this where your parameter space is basically the space of density matrices, and your loss function is usually fidelity or something, and you receive many copies of a parameterized state where the parameter is literally the density matrix itself. Then you make a bunch of measurements, and then you make a guess of what you make a guess of what the state is. It's in general, that's a very hard problem. It takes exponentially many copies to kind of get anywhere, and also because it's not a classical problem, there's no optimal way to do it. So shadow tomography is a way to do it, but you can come up, because it's not optimal, you can always come up with other strategies that have a chance of doing better depending on what the underlying parameter is. It usually probably doesn't make sense to view full state tomography as a parameter estimation problem because we kind of care about different things there, but it is a special case of this. Yeah.
So does your conclusion can help the problem classical? I mean, do your conclusion can like give some hint, give some hint of those strategy to classical shadow tomography?
I'm not entirely sure I understand the question, but our conclusion is basically that there's no optimal way to do state tomography.
Okay.
There's no best way. You have to make, yeah.
So you have to make at least some approximate optimal. So you have to know in advance how to approximate in which way, right?
Yeah, you can hope for something that's approximately optimal, and in the case where you receive kind of n tending to infinity copies of your state, I would expect that there would be some approximate thing, but I haven't proved anything like that, so I can't claim to know for sure. But I'd expect that you get something approximately optimal, and probably reasonable stuff like shadow tomography is approximately optimal in the limit of n tending to infinity.
Okay, I see. Okay, thank you.
Thank you. Any other questions? I'm greeted by a wall of silence and black cameras. So,
is there any question from the audience?
Sorry, maybe another question. Probably you already answered this earlier, but I'm still curious for some non-convex, non-convex like some part of the theta is convex and some part of the non-convex. Is there any this kind of example? I mean, tensor product.
So so I can give you one example of a non-convex loss function. So the what's called I'm going to mispronounce this name, but something like Bhattacharya distance. So that would be, it's a distance between two probability distributions. So if these if your parameter space was the space of probability distributions, then the Bhattacharya distance is the sum of the products of the square roots of the entries in the probability distribution. That's not convex. I have struggled, other than that kind of example, to find one that people use that isn't convex.
So you think the non-convex problem to find the optimal strategy is a good direction? Do you think that?
Yeah, I mean, it would be interesting to think about. I don't know what you would. Yeah, I have no intuition for what would happen in the non-convex case. It's probably interesting to think about. I think before I would want to go away and find some more examples of non-convex loss functions, just to physically motivate it. But they probably do exist if you look for them. Yeah.
And for non-convex set is more common, or the non-convex function is more common in a physical?
The non-convex set condition can be weakened. So I would not explore the non-convex set, because if you look at the proof of the theorem in the paper, and we kind of mention this, you can almost this condition can be weakened and be made kind of for any. You'd have to pick a very pathological set for this not to be true. For the loss function, I don't know what would happen. So that's probably a better direction to look.
I see. Okay, thank you very much.
Thank you.
Okay, is there any questions? Okay, if there's no further question, thank you, Salmon. Thank you for today's talk. Yeah.
Thank you very much. Thank you for having me. Thank you.
Thank you.
Thank you.
Bye.
Bye.
Thank you.
Bye.
Bye.